Hello and welcome. Today we will introduce our recent published work in the ICML towards neural architect search through hierarchical generative modeling. Well, neural architect search brings a lot of advance in the network performance in the recent days. But one challenge is significant in the NAS task is that with increasing of the search space, the cost of search is significantly increased. The key of this problem is that we even evaluate single network could be very challenged. So with search space increasing, the evaluate cost increase significantly. So we don't want to spend our GPU resource to evaluate the network so we propose this method that use the generative model to help us to quick generate the elite candidates that can be evaluated based on the users. So we get this inspiration from the recent advance in the language model. In the language model, we know the word embedding makes words with similar semantics that closed in the vector space, and an unseen word with similar subwords will also consistently have similar semantics. And in the downstream task, if we have two unseen sentences with similar average word embedding, we consider them have relatively similar overall semantics. While in the neural network, we always arrange the neural network as a sequence of blocks. So can we have such embedding, like the word embedding, make the neural network to have similar word embeddings that have similar performance to accelerate the neural architect search? We start design this idea with design the network graph encoding space. To include as much as possible network graph and blocks, we design a loose constraint graph design space as follow. So in this graph net design space, we have 6 intermediate nodes between input and output. The node only allowed to get connect from the previous node and avoid the cyclic graph. We also include the following operation with different kernel size as candidates. It should include all the basic operations that has been introduced in the existing applications. So to design a network graph variation encoder, we call it GVAE. We encode operations into one hot vector matrix and the collection of the graph into adjacent matrix. So the best practice to encode such graph representation is to use graph convolution network to embed the graph into the vector space. The GCN training objective is listed as follow. We start with training with very fundamental BCE loss to make sure that VAE can encoding the graph and then decoding with reconstruct it. Then we use KL divergent loss to regularize the VAE training to make sure it's generalized for the unseen graph. And we also introduce this triplet loss to make sure the network with similar zero cost, they can cluster with each other. So to make sure that the network has expected similar performance or similar cost can be clustered together with each other. To enhance this property, we also use this predictor as MSE loss to predict the performance of the network. So we can see with this triplet loss and the semi-supervised learning, the GVAE significantly improved in its property that clustering with network who have different costs parameter size, and the performance. So once we have this latent space that clustering the network with its zero cost, considering has different performance and have different costs, we want to sampling over this latent space. Since the GVA space is high dimension and complex, and the boundary of each cluster in the embedding space is unclear, to best sample over each cluster, we introduce this conditional continuous normalized flow to sample on the complex distribution. Conditionally continuous normalized flow is an advanced deep learning techniques that extend the concept of normalizing flow to handle the conditional distribution, enabling more precise and flexible modeling of the complex continuous data in a variety of contexts, particularly in the scenario where the data distribution is dependent on the center condition or parameters. So we train the CCNF with following objective. Now, we want to introduce our overall framework for the hierarchical network modeling. Now, I will introduce our overall framework of our hierarchical network generation process. So we start with a very initial large search space that without mask constraint. As we introduced before, we call it GraphNet. And we train a graph variational autoencoder based on it, and with in a semi-supervised manner with the triplet marginal loss with that as we designed, and with predict loss. And in the graph variational autoencoder latent space, the network graph that has different performance, different zero cost matrix, and parameter size will be clustered into different clusters. We use Gaussian mixture model to identify different clusters in the latent space, and we train a continuous conditional normalized flow to generate the signal cell arc based on it. So the continuous conditional normalized flow allow us to sampling over different clusters based on single conditions that by simply sampling over a Gaussian distribution. So with this ability, we can generate the graph from different clusters. We can use this cluster ID as the symbol of macro architecture generation. So we can exploring the macro architecture design space with agent evolution and only mutation on the type of the cell, and create this architecture with continuous normalized flow. So we're exploring the enough sufficient sample of this macro sequence, and we train a sequence generator that with the architecture and zero cost matrix pairs to generate to create a generative model that can generate architectures given the condition of the zero cost matrix and tokens. So with this generator, we can generate final models from the architecture that's generated from the sequence, and use the CCNF and the GraphVAE to generate the detail of the microarchitecture in each cell. So we compared with the previous methods, NAS approach that used the zero cost and agent evolution to search over a large search space. we can see in the previous work, like GenNet, use a lot of predefined hyperparameter to limitate the design space, and it spent exhausted iterations in the agent evolution method to search for the best network with highest zero cost matrix. And the works very well. This method works very well, but it required a lot of time to evaluate over those networks. So it's expensive, even it's evaluated in the zero cost manner. So in our GraphNet search space, it's NAS constrained, it's NAS predefined. We can see with this agent evolution method, we can still have some good performance, but compared with the previous approach, such loosely constrained search space makes the performance decrease because it's not sufficiently, even with such huge number times of search. So we use our hierarchical generated method. We start with use the high-level evolution on the T sets and use CCNF to generate like 20,000 samples. We can see compared with traditional agent evolution, we can find much better network in this GraphNet space. And with sequence generator and continuous normalized flow, only generate 100 candidates. Given the condition we have provided, we can find much elite network compared with previous agent evolution method.